Welcome to the beginning of the third module. We'll start with our study of statistics and data analysis by doing visual analysis of data. This can be thought of as kind of like a first step for any sort of analysis of data. Before you start crunching numbers and trying to get too quantitative, it's good to do something a little bit big picture related. Try and find like a nice graphical representation of your data to find any big picture trends. Then you can use statistics to be more precise and refined about the types of claims you want to make. So this is typically, again, a first step. It's not the most important thing necessarily, but it helps you from making any big overstatements or mistakes about your data. Kind of puts your statistical analysis in context. On the CLEP, they're going to potentially ask you about a variety of graphical representations. You should be familiar with many of the standard ones. We'll review them today. Two that are very standard are the related bar graphs and histograms. You've seen these before, certainly. The only real difference between them is that bar graphs are typically used for data that counts the number of things in a given category, while histograms are used for the number of things in a given numerical range. From our standpoint, there's essentially no difference. These are very subtle points that really only technical experts care about using the right name for. One thing to notice is that bar graphs typically have spaces between the bars, whereas histograms do not. Whether this is important or not, it's sort of up to your tastes. For me, there's not a whole big difference in that regard. Another type of representation you should have some basic familiarity with is the pie chart. Again, I'm sure you have seen this before. The idea is to take your categories and to fill segments of a circle in proportion to their appearance. The idea here is you take data on group 1, group 2, and group 3, and represent them in proportion in this chart. Nothing too complicated about it. Let's look at an example where we're asked to create a histogram and a pie chart from some simple data. Our data is, we survey 200 people and ask them about their favorite color. Our results are 33 people say blue, 50 say green, 17 say red, and 100 say yellow. Keep in mind that this is clearly what you might call synthetic data. The fact that I asked 200 people and only got 4 answers about what your favorite color is indicates this is probably not accurate. For example, no one said anything like purple or orange. In reality, you would expect the data to have many categories with very few responses. Some people may say something strange like lavender or maroon. We're going to ignore the fact that real-world data is almost always more complicated than the type of data generated for these examples. We're just using this data to make an analysis of these charts. So what do? Let's start with the histogram. So note that the proportion of blue is 33 in 200. The proportion of green respondents is 50 in 200. The proportion of red respondents is 17 in 200. And the proportion of yellow is 100 and 200. So what this is about 0.25, well, it's exactly 0.25. This is exactly 50. This is something like 0.17. And this is something like 0.8. So I'll plot these values for the histogram. All right, so blue should be somewhere like 0.17. The green should be at 0.25. Notice that there's no spaces between the bars because it's a histogram. For red, we're at about 0.8. And for yellow, we're all the way up at 0.5. Okay, so not too bad. And then for the pie chart, we want to cut out slices of this pie in proportion to the proportions I just computed. So yellow should be half of the pie, green should be 1/4 of the pie, and the remaining quarter should be split between blue and red. So let's do that. Let's start by saying this is yellow. Then we'll cut here and say that this is green. And then, oh, I don't know, something like this maybe. Without a computer, one can only be so precise. So that's 0.08. Red. Okay, so, one can look at the bar graph and say, well, clearly yellow is the biggest, highest proportion. But the pie chart also contains useful information. It tells us, for example, that the proportion of respondents who said red and green, or either one of those, is equal to the amount that said, the respondents who said blue or red is equal to the number of respondents who said green. And the number of respondents who said red or blue or green, all of them together is equal to the number of people who said yellow. You wouldn't necessarily see that from the histogram, but it is contained in the kind of geometric structure of the pie chart. So that is a useful benefit of it. A type of graphical model that can be very useful, especially when you have data corresponding to time values, is the line plot. So for this, it's, I think, in some ways the most simple. You plot your data points, and you connect a line between them. And try and infer a pattern from the line. Sometimes the pattern is very clear from the line. For example, I will cook up some synthetic data here where looking at the pattern from the line is very suggestive of what's happening. For example, suppose your data looked something like the following. Okay, so if I have these data points and I fill in line segments to connect the points, then I get a sense that, okay, what I have is data that grows across the x-axis. And what is the rate of growth? Well, it looks very rapid. This might even be suggestive of exponential growth. That is, this data certainly leads us to believe that that's a possibility. Whether it's true with high probability is something that is very possible to study with statistics. In fact, it's one of the fundamental questions. Given the data, how confident are we that it follows a certain model? We do not do that in this class. This is called statistical inference and is a huge field of study. Certainly something you will get to in a freshman year or a second year of college statistical course. Okay, so I will just remark that the line plot here suggests exponential growth. And this is one of the best properties of the line plot. When you have data that's amenable to it, it makes it very easy to see the patterns. So when I'm working with my real-world data and my machine learning research, this is one of the first things I do. I take the data and I try and plot it in a simple way like a line plot and try to discover if there are any basic obvious patterns. If yes, you can try and do a more thorough analysis and try and confirm that it is actually exponential, for example. If there's no obvious analysis from the line plot, well, then you have to be a bit more clever. Unfortunately, this is more often the case than not. The last type of graphical method I would like to look at is what's called a stem and leaf plot. I find this rather odd. I've never really used it personally, but it is something that could come up on the exam. Essentially what we do is we sort the data and organize it by first sorting by the tens or the hundreds digit, and then sorting by the tens or the ones digit. So I think this is best illustrated with an example. So here we have a small data set, and I'd like to create a stem and leaf plot. So this is supposed to organize for us in the following way. On the left column here, I will write all of the possible tens digits. So there could be a tens digit of 0. I see some tens digits of 1s and some 2s. And then I sort within the ones digit. So what numbers have tens digit of 0? Well, this would be 6, 2, 3, 6, and 8. So now I organize those and I go 2, 3, 6, 6, 8. And then I move on to tens digit 1. So 12, 15, 11, and 12 again. So I put 1 there, 2, 2, 5. And then lastly, tens digit 1, tens digit 2. I already did tens digit 1, 24, and 23. So 3 comes before 4. So all I do is I try to say, look within a fixed tens digit. If I know the tens digit is 0, what does my data look like? Well, I see that I have 6 twice, a 2, a 3, and an 8. And then I play the same game for all the possible tens digits. So the idea behind this representation is it tells you sort of where most of your data points are. I can see that I have more data points with tens digit 0 than I do with tens digit 1 or 2. So this suggests that most of the data is congregated closer to 0 than it is to, say, 20. So it can be useful in that regard. I personally find it to be kind of not the most informative, but it is something that the CLEP can ask you to do and is very standard in even freshman level statistics classes. So something to be familiar with. Just because I don't find it to be particularly useful in my research does not mean it's not an important technique for you.